Hi, good morning to everyone. Welcome to my channel Elecom Edu. By this session, you are going to learn negative numbers and their arithmetic and floating point representation. The agenda of today's session. By this session, so what we are going to cover and what you are going to learn. It is a 5 sections. So section 1, why we are using the signed numbers. The simple definition I have given here, the problem binary integer phase representing negative. We will see in detail. In section 2, you are going to learn what is sign magnitude. So from here itself, you can find it is the simplest scheme. So from that word itself, you can understand sign plus magnitude. And section 3, it is a ones complement. So complement means it is an inversion. So bit to be inverted. One time inversion. And section 4, which is a 2's complement. So 2's complement, it is a universal accepted standard which is used in every modern CPU. We will see what is meant by 2's complement. And the last section that I considered as a part 2 of today's topic, IEEE 754 floating point. So how to represent the real numbers? By the definition as sign, exponent as well as matrix. We will see one by one. Right. So this is a section 1. In the section 1, why we are in need of the signed representation. Right. So you already know computers can able to store the information as binary digits. So the binary digits are bit 0 as well as bit 1. There are two types of representation. One is a signed representation and another one it is a unsigned representation. So if you consider the unsigned representation, that unsigned representation can also be termed as a plain binary. You can see in the slide, I represented it as a plain binary. The plain binary is nothing which is an unsigned representation. So this unsigned representation or plain binary can only express zeros and positive values. But in reality, we are in need of negative numbers also, constant need of negative numbers. I have given you the 3 examples there. The first example, I represented the temperature, right? In cold countries and all, the temperature is below 0 degree. So at that time, we used to represent it as minus 5 degrees Celsius or negative temperatures. So in the scenario, it is must that we have to use the signed numbers. And in the second case, I have given you the bank balance. So if suppose you are using a bank balance overdraft, if your bank balance is overdraft, so at that time in your statement, you used to get it as minus value. So here I represented it as minus rupee 1200. And a subtraction result. See, if it is 8 minus 5, the result is 3. It is a positive value. If it is 5 minus 8, I mean the least number, difference between the least number and the most number, it is minus 3. So here also we are in need of the negative numbers. So in reality, we are in need of the negative numbers. That's why it is must that we need a signed representation. In the signed representation, there is a universal rule. That universal rule I have given like as most significant bit is reserved as a signed flag, and the values I have given it as 0 and 1, positive number as well as the negative number. Right? I want to recollect you some point here. So in the earlier 2 sessions, in the earlier 2 topics we discussed in the 2 modules, I told you What is the most significant bit? What is the most significant bit? The leftmost bit is the most significant bit. For example, you are using a byte. So byte in the sense, how many bits will be available there? 8 bits will be available there. Bit 0, which is the least significant bit, it will be available in the rightmost side. While you are increasing the bit value one after another. So where the bit will be completed? Bit 7, because you started at bit 0 and it ends at bit 7. So that bit 7 is the leftmost bit. Whenever you are considering any signed number representation, the most significant bit will act as a signed bit. So how many signs are there generally in the universe? One is a positive sign and another one it is a negative sign. If the most significant bit is having the value 0, we used to call it as a positive number. The same, if it is having a 1, we used to call it as a negative number. This is applicable only for signed number representation, not for unsigned number or plain binary. So, there are 3 classical schemes. These 3 classical schemes differ only in how the magnitude of negative number is stored. So, the 3 classical schemes are 1's complement, 2's complement and the floating point. So, we will see in the forthcoming session. In the section 2, you are going to learn what is meant by sign magnitude representation. In the agenda itself, I told sign magnitude representation. So sign plus magnitude. Please check that register whatever I mentioned there. Register, already you know what is meant by register. Register acts like a container where you can able to store the values there, right? So just to find how many bits are there in the register. 1, 2, 3, 4, 5, 6, 7. So 7M and 1. Yes. In the color code I represented, M's are in the blue color. So that is bit 0 to bit 6. Those are the magnitudes. So how many magnitudes are there? 7 bits as a magnitude. And the last one, I mentioned it as a S. So S means it is a sign. Where that S is available in your MSB, which is your bit 7. So this register, whatever I mentioned here is a signed magnitude. So sign is available as well as magnitude is also available. Kindly recollect the universal rule. If S is equals to 0, this register is a positive register. When S is equals to 1, this register is a negative register. Right. And here in the next, the right side, you can see I have mentioned it as a range. Range for n bits. So how many bits I am considering? Byte I am considering. So byte in the sense it is 8 bit. For n is equals to 8, the overall formula, please remember, minus of 2 power n minus 1 minus 1 to plus of 2 power n minus 1 minus 1. So 2 power n minus 1. So 2 power n minus 1. So 8 minus 1 is 7. So 2 power 7 minus 1 should consider the negative value to 2 power 8 minus 1. 2 power 7 minus 1 should be considered the positive value. So what are the ranges there for your signed magnitude? Minus 127 to plus 127. Please check over the examples of 8-bit. So here I have taken 2 values. One is a 25 plus and minus. Next it is a 0 plus and minus. It is so surprising, right? There is a 0, but we have written it as plus 0 and minus 0. But you already know 0 don't have any signs. So that is the first limitation here. We will discuss what are the limitations. Okay, first check your first row and first row. In the first row, what I mentioned, it is plus 25. In the second row, I have mentioned it as a minus 25. It is a signed bit representation. So if it is a signed bit representation, first what you have to do? You have to write the sign. Already you know 0 is for positive and 1 is for negative. So the way I have represented it as 0 for positive and 1 for negative. Next I have to convert this 25 into binary. Try to recollect how to convert the decimal to binary. Good. It is a continuous division. So 25 divided by 2 continuously, right? Please check this from the LSB. So what is there in your LSB? Bit 0. What is there in your earlier MSB? It is 2 power. It is a 6. So it is a binary. Means that 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5 and 2 power 6. So 2 power 5 is having the value. So what is 2 power 2 power 4 is having the value. What is 2 power 4? It is 16. What is 2 power 3? It is 8. So 16 plus 8, 24. And what is the last value? 2 power 0, 1. So 24 plus 1, it is 25. But you are writing it as a plus 25. How you are telling it as a plus 25? Because the signed bit MSB, that is 2 power 7, is 0. Next consider minus 25. So 25 is exactly same, 0, 0, 1, 1, 0, 0, 1. But I am mentioning the negative sign there. What is my negative sign? Minus. Next come to the complicated 0. Why we called it as a complicated 0? Because it is plus 0 and minus 0, right? 0 means all the values will occupy the off condition. So I have 7 zeros here, 0, 0, 0, 0, 0, 0 and 0, 7 zeros. But it is a positive 0. That's why MSB I have made it as a signed bit 0. And after the slash I mentioned 1 because I am considering it as a negative 0, right? See, this is so surprising, right? So what we did here? No use of this code, right? Because 0 is 0 only. Then what is the necessity of making it as a positive 0 and negative 0? That is a complicated comparisons here. It is waste of code, right? That is the first point. Second limitations is, the second limitation I am mentioning here is, see, you have to do the addition and subtraction, right? So whenever you are doing addition and subtraction, whatever system or circuit you are designing here, it has to check over your sign every time, whether that is a positive value or else it is a negative value. The way your circuit also becomes complicated, right? These are the limitations of your sign magnitude representation. So to overcome this sign magnitude representation, we are going into the section 3. The section 3 is a ones complement representation. Already I told you what is meant by complement. What is meant by complement? Inversion. Kindly remember. Complement is nothing, it is an inversion. So ones complement in the sense one time. Every bit should be inverted. So if you do that one, we used to call that number as a negative number. Generally, in the decimal, how will you write your positive number? Plus 25. How will you write your negative number? Minus 25. So in the ones complement, instead of doing it as a minus 25, we have to do the inversion of every bit, 0 to 1 as well as 1 to 0. That's what I represented there. Negative numbers are formed by inverting every bit of the positive binary value. So again check this example, plus 25. In the earlier slide itself, you checked how to represent the plus 25. The MSB bit is 0. 0 represents that it is a positive value. Where and all you will get the on state 2 power 4, 2 power 3 and 2 power 0. So 0, 0, 1, 1, 0, 0, 1. This is plus 25. Now you are going to apply the ones complement to this plus 25 to convert it into minus 25. So what is a ones complement? 0 should be converted to 1 and 1 should be converted to 0. So I mean it is a inverting. So first check your LSB. In plus 25 it is 1, but in minus 25 it is 0 because inverting of 1 to 0. Check your second bit, 0 converting to 1. Third bit 0 converting to 1. Fourth bit 1 converting to 0. Fifth bit 1 converting to 0. Sixth bit 0 to 1. Seventh bit 0 to 1. Eighth bit 0 to 1. So now whatever represented here in minus 25, 111, 00, 110 is nothing. It is a ones complement of the plus 25. Again, you have to check the range. Okay. So how many bits we are considering? 8 bits we are considering because we are considering all our registers as 1 byte register. Right. Here also the ranges is minus 127 to plus 127. So how you got that minus 127? Minus of 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. So whatever you have checked in your earlier slide, right? Here, what are all the things you have to check it as a key feature or the limitations, right? The first limitation is still it is having two zeros. I mean plus 0 as well as minus 0. Nothing changed between the signed magnitude representation towards your ones complement representation. There in your signed magnitude representation, 0 you have considered it as plus 0 and minus 0. In ones complement also you are considering it as a plus 0 and minus 0. So the ambiguity remains the same. The second problem here happening is end around carry. Right? Okay. I hope you remember these two words whatever we have checked in your earlier classes. Overflow and underflow. Right? Okay. What is the overflow? Yes, absolutely. So overflow in the sense the value which is overflowed when you are writing it inside the register. For example, in the 25, in the plus 25 or minus 25, you can consider anywhere. So how many bits are there? Only 8 bits are there. If suppose I am getting the ninth bit, whether I have the container to place that? No. So on that time, we used to call it as an overflow, right? Okay. So if it is happening in that way, in the ones complement, what you have to do? You have to take that end around carry. You have to add that with your LSB. That is your end around carry because that carry is overflow. So you can't able to leave that carry as such. Instead of that, what you have to do? You have to bring that end around carry, that overflowed carry to the LSB, and the LSB will be added with your end around carry. Right? Okay. So subtraction via addition needs any MSB carry out added back to the LSB. Right? So that is your first one. End around carry is the problem here. Next one, it is a moderate hardware. But when compared with your signed magnitude, here it is the simplest one. But what is the one limitation here? You have to do the addition of end around carry. It is one more addition representation, right? So on that time, what will happen? You have to take one more extra step to add the end around carry to your LSB. So at that time, automatically the delay will be happened for completion of this part. Okay. So that's why signed magnitude, when compared with the signed magnitude, one's complement is simple, but it is a time representation. So time will be more. You have to take more time to complete. That's why to overcome this problem, we are going into the next section, that is a section 4. So the section 4, It is a 2's complement representation. So remember, 2's complement representation is a perfect industry standard, right? Okay. Already you know 1's complement. What is a 1's complement? Inversion of 0 to 1 and 1 to 0. So 2's complement is 1's complement plus 1. First you have to take the 1's complement, then you have to add 1 to the 1's complement. While adding, you have to choose that position as a LSB, right? That is your 2's complement. That is 1's complement plus 1. Again, the same example we can consider plus 25. So what is plus 25? It has to start with 0 because it is a positive value. Where you will get the 25? 2 power 4, 2 power 3 as well as 2 power 0. The way I have written it as 0, 0, 0, 1, 1, 0, 0, 1. Next you have to take the 1's complement. What is a 1's complement? 0 to be converted to 1 or inverted to 1 and 1 to be inverted to 0. So first 3 zeros will become 3 ones. Second, next set of 2 ones will become 2 zeros. Next set of 2 zeros become 2 ones and the last one will become 0. So you did the 1's complement. After that, what do you have to do? You have to add 1 with the 1's complement. Where you have to add? You have to add with your LSB. What is there in the 1's complement? LSB 0. So 0 plus 1 is 1. The other values and all will be coming as such. So what is the 2's complement? 1, 1, 1, 0, 0, 1, 1, 1. So this 2's complement is again minus 25. Right? Okay. What is the one difference there? You have add 1 with the least significant bit. So you are adding 1 with the least significant bit. So that's why here the range is getting changed. In the earlier two cases, what are your ranges? Minus 127 to plus 127. But here what is the range? 1 is getting added. So means that 1 bit is getting added. That's why it is minus 128 to plus 127. Right? Okay. So here we used to call it as a asymmetric representation. Right? Okay. Why we have to use the 2's complement? What is the first limitation there in your sign magnitude? Plus 0 as well as minus 0. What is the problem available there in your 1's complement? Plus 0 and minus 0. But here only 1 0. There is no positive value in 0 and no negative value in 0. Only it is 0. So there is no signed bit here. Everything is only the magnitude. Right? Right. What is the second advantage there? A second disadvantage there in your 1's complement? End around carry. So what happened? If the carry is overflowed there in the 1's complement, you can't leave as such. What do you have to do? You have to bring that end around carry to your LSB. You need to add and you have to complete the result. But in the 2's complement, if end around carry is there, you can discard that carry. So no end around carry, the overflow bit is simply discarded, right? What are the other limitations you check there? For just to check your first one, sign magnitude. In the sign magnitude, what I said, complicated device. Why the device or circuit is complicated? You have to check, you have to design the circuit for addition separately as well as subtraction separately. Because if it is addition, the magnitude will be available same, but the sign bit is 0. If it is a negation, the negative value, the signed bit is 1 and the magnitude will be available same. But here in the 2's complement, only one circuit is enough to do both the addition operation as well as the subtraction operation. So same adder circuit for addition as well as the subtraction. And the very best usage or advantage of this 2's complement representation is it is used in every modern CPU or ALU. So CPU and ALU follows only the 2's complement. So there is no signed magnitude or else there is no 1's complement. So all the CPUs in the current scenario using only this 2's complement. That's why we used to call it as a industry standard. And we will check the comparison of that, right? Okay. What is the first feature? Negative rule. So if it is a signed magnitude, how you are classifying the bit? Signed bit as well as the magnitude bit. So signed bit occupy one position, I mean one bit. The bit will be 0 or 1. If it is 0, which is a positive value, 1 which is a negative value. If it is a 1's complement, what you did? You invert all the bits, 0 to 1 and 1 to 0. If it is a 2's complement, 1's complement plus 1. So 1's complement is nothing, it is inversion of all bits. Next, check over the range. So in signed magnitude as well as 1's complement, what are your range? Minus 127 to plus 127. But in 2's complement, you are adding 1. That's why it is minus 128 to plus 127. Next is zeros, right? In signed magnitude as well as 1's complement, 0 is having a positive value as well as negative value. So two zeros comes into the picture. But in 2's complement, it is having only 1 0. And hardware representation, arithmetic hardware. Signed magnitude, it is a complex. The reason is you have to design a circuit for positive number separately as well as negative number separately. In 1's complement, one circuit is enough. But what is happening there? Time delay is happening because of end around carry. But in 2's complement, it is very simple because one circuit can able to do both the addition operation as well as the subtraction operation. Used in CPUs and ALUs, signed magnitude, never. 1's complement, rare. But 2's complement, yes, it is a universal representation. Here I have given you the representation of range by scheme. It is some visualized part. I hope you can remember. I have used two colors. Okay, one is a blue color and another one it is an orange color. This blue color is a maximum negative value and orange color is a maximum positive value. You have three schemes, which is the one I have discussed in the first slide. One scheme is a signed magnitude, second scheme is a 1's complement, and the third scheme is a 2's complement. In 2's complement, negative is minus, 128 and the positive is plus 127. Why it is happening here? Because 2's complement is nothing which is 1's complement plus 1. But in the signed magnitude as well as 1's complement, negative as well as positive, both are actually 127 only. So minus 127 to plus 127 as well as minus 127 to plus 127. So 2's complement reaches one extra value on the negative side because it has no wasted minus 0 code. Okay, that is a part 1. So in part 2, you are going to learn about floating point representation. The floating point representation is nothing, it is a IEEE 754 basics. So this IEEE 754 basics actually representing real and fractional numbers in the binary. We will see what is here and what you have to learn from here. Okay, right. So why do we need a floating point? Right? Okay. So whenever you are considering any values, there is not only available the integer representation. Most of the places there is available the fractional representation also. Right? So if you are considering the computers, if you are considering the normal data everywhere, it is a combination of integer part as well as the fractional part. That fractional part is nothing which is a floating point. Okay. So integer, if you are considering the integer scheme, there won't have any fractions or very large or very small magnitudes, right? I have given you some examples here. You can check over here. The first example I have given it as 6.022 into 10 power 23. See here, 6 is the integer part, 0.022, which is actually the fractional point, I mean the floating, into 10 power 23, means that that is an exponential, right? So this is the way how we are doing all the scientific notation. So floating point stores numbers like a scientific notation. The second example I have given a small measurement, 0.0000001, right? In the third, I have given the number with the floating point, that is a value of pi. So the value of pi, generally we are taking it as 3.14, but it is not a completed value. 3.1414159, it goes on. So whenever any numbers you are considering in the real-time scenario, it is having a floating point. So floating point should be represented very clearly. So to make that clear representation of floating point, we are following a particular standard. That standard is nothing which is your IEEE standard. We will see what is that IEEE standard. Okay. Next, check this blue box. In the blue box, I have given you the general form. I mean the general form of floating point. Value is equals to minus 1 power s into 1 dot m into 2 power e minus bias. So minus 1, it is a numerical value. Leave that. Yet s represents that it is a signed bit. So what is a signed bit? 0 as well as the 1, which is your MSB. Remember? Yes. If it is a 0, that is a positive value. 1, that is a negative value. Next, 1 dot m. So that dot is nothing which is a floating point. Okay. So m. The m represents the mantissa. The mantissa is nothing. It is a fraction after implied leading 1. So mantissa is nothing which is a fraction point. I mean the floating point. Next, 2 power. Okay. E minus bias. So E is nothing which is a biased exponent. Right? Already I said. How to write this 10 power 23? 10E23. That E is nothing which is a biased exponent. Minus bias. What is a bias? It is a fixed offset. So exponents stores as an unsigned number. This bias is a fixed value. By next slide, I will tell you what is that fixed value and why should. So it is a fixed offset. If you consider that bias is a fixed offset, so the exponents stores everything as a unsigned numbers. Okay. Already I told, whenever you are making this floating point representation, you have to follow some format or standard. That format or standard is IEEE 754. In that particular format, you can take two precisions. One is a single precision and another one it is a double precision. So please check over all the columns. The first column is total bit. The second column is sign. The third column is exponent. Fourth column is mantissa. And the fifth column is bias. So the total bit, remember 32 and 64. Single precision it is 32. Double precision it is 64 because 32 into 2 64. Other and all what we checked in the earlier, the format, right? What is there in the first format? Minus 1 power s. What is that s represents? It is a sign. So I have given the sign. Already you know sign. So sign means it is a only one bit. Where that bit is available? In your MSB. That bit value may be 0, otherwise the value may be 1. If it is 0, which is a positive value, 1, it is a negative value. So it may be the single precision or double precision. Sign bit is a 1 bit representation, right? Next you have read it as 1 dot m. So what is that m represents? It is a mantissa. What is that mantissa? So after that 1, how many number of fractions leaded? How many number of fractions lead they? That is actually mantissa. If it is a single precision, so how many mantissa bits should be lead after the one? 23 bits. If it is a double precision, how many should lead? It is 52. Right? Okay. What is the next one you learn? 2 power e minus b. Right? So what is that e represents? It is an exponent. Right? So for single precision, the exponent is 8 and double precision, the exponent is 11. The last one is a bias. So bias is nothing, it is a fixed offset. So what is a fixed offset for single precision? 127. For double precision, it is 1023. Right? So based on this, I have drawn the single precision bit layout for you. So what is the total number of bits in the single precision? 32 bits, right? In the 32 bit, 1 bit is a signed bit, 8 bit is an exponent bit, and the remaining 23 bits are the mantissa bit. So remember, mantissa should be started from the LSB. So 0 to 22 and so 0 to 22 means it is 23 bits. So from 23 to 30, which are your exponents, right? The MSB, which is your signed bit, 31. So 0 to 31. If it is a double precision, the structure is exactly same. Instead of exponent 8 bits, there the exponent will be 11 bits. Instead of mantissa 23 bits, it will be greater than 23 bits, I mean the 52 bits, right? I hope till this it is clear for you, right? Then we will see that visualization structure, whatever you studied there, okay? So here I have given you only the two representation. One is your exponent and another one it is a mantissa, because there is no difference between your signed bit. That's why I didn't consider that one, okay? Right. Here, the double precision spends its extra 32 bits mostly on mantissa, right? That's why it always the accuracy is very, very good there in the double precision when compared with your single precision. So that's what buys the added decimal accuracy. So if you want to do the decimal representation to be the accurate format, instead of using the single precision, you can go into the double precision. Okay, right. So how many exponents there in your single precision? It is 8. So how many there in your double precision? It is 11. What is your mantissa there? It is 23. What is your mantissa there? It is 52. So the value will be 0 to 64. Here the value will be 0 to 31. So means the 32 bit as well as the 64 bit. Okay. And sign you check. How many bits are there in the sign? Only 1 bit. So that's why a very, very thin orange color I represented for the sign. So both sides it is 1, 1. And blue color 8 and 11. One more light blue color, I represented it as 23 and 52. So this is a visualized representation for the value format, whatever you checked over there. Okay, right. So we will check one small example for this mantissa representation. I mean your floating point. Okay. So convert 10.5 to IEEE 754 single precision. I am considering only the single precision. So remember, single precision is 0 to 31. I mean the 32 bit, right? Okay, right. So what is the first thing you have to do? What is 10.5? Yes, absolutely good. So what is 10.5? It is a decimal value. So you have to convert this decimal value to the binary value. So in the 10.5, so earlier to the dot, I mean the decimal point, which is a whole number, integer part. After dot, 5, which is a fractional part. So how to do the conversion? 10 should be continuously divided by 2 and 5 must be continuously multiplied by 0.2. That's it. I hope you remember that. Okay. So 10 divided by 2. 10 divided by 2, you are getting it as 1010. So 10 divided by 2, the value will be 50, right? So the one remainder is 0. So 5 divided by 2, 2 2s are 4. The next value is 1. Again 2. 2 divided by 2, it is 10. So what is the value? 1010. How you have to write? You have to write from bottom to top. What is the next value? 0.5. So 0.5 into 2, 1. So what is your carry there? 1. So 1010.1, that is your first step binary conversion. So next step, what you have to do? You have to normalize this. So for normalizing, what I am doing? I am going into my exponent part. What I am doing? I am going into my exponent part. So what is the exponent I have taken? I have taken my exponent as a 3. So means that the decimal point should be lead to 3 points earlier. So instead of writing 1010.1, I have written it as 1.0101 into 10 power 23. Right? 1.0101 into 10 power 23. Sorry, 1.0101 into 2 power 3. What I have written? 2 power 3. Right? So what is the 2 power 3? The 3 represented as an exponent there. Okay. Next, I have to add bias. Remember what you have did in that E and B? So you have to use it E and B. What is your E here? 3. What is the bias for your single precision? 127. So 3 plus 127 is 130. Again, this 130 is a decimal value. So you have to convert it into binary. So continuously divided by 2. The value is 1, 0, 0, 0, 0, 0, 1, 0. Now I have to determine the sign. Check your number. What is your number? 10.5. So means that it is a positive value. So sign is a positive sign. So what is the binary for your positive sign? It is 0. So I have written it as a 0. So in the orange color, it's a sign bit. The bit representation is 0. What is the next one you have to write? You have to write the next one as an exponent. What is your exponent? It is 2 power 3. Because how many decimals you shifted? 3 decimals you shifted. So that is 1 point. Because what is your second value? 1 dot of m. What is your second value? 1 dot of m. Please recollect the values. Minus 1 power s into 1 dot of m. So what is your m here? 1 dot of m. Exponent, how many you needed? 3 you needed. So what is the value of that 3? It is e plus b. So the value is 1, 0, 0, 0, 0, 0, 1, 0. That is the value 130. So after that, what you have to do? You have to write the mantissa. So what is the mantissa for your single precision? It is a 23. Good. 0 to 22. What is a mantissa for me here? 1 dot of m. What is your m? 0101. So how many values are there? Only 4 values are there. But how many values you should get? 23 values you should get. So the remaining L should be appended with a 0. Whatever I have taught you there in the conversion. In the conversion I told, if the register which don't have any values, you can't leave the register bit as such. Instead of that, what you have to do? You have to append or pad the 0. So for the mantissa, you supposed to have 23 bits. But I have the mantissa only 4 values. That's why what I did, I have appended the remaining zeros here. So in the step 5, I assembled it as a 32 bit. So see here, 23, I mean 0 to 22. Here it is 2 power 3, 8 bits here, 2, 4, 6 and 8. And last one it is 1. So it is totally of 32 bits. Right? Here, I will tell you some special values in IEEE 754. Check here, if your exponent is 0 as well as mantissa is 0, the value is 0, right? If your exponent is all ones and your mantissa is 0, it is an infinite value. If your exponent is all ones and mantissa is not equals to 0, it is NaN, means that not a number. It is not a number. N, not a, again the N, it is a number, not a number. So these are the special values there in the IEEE 754 standard. So what is the standard you have to follow for your floating point representation? Minus 1 power s, 1 dot m, and you have to use the 2 power e plus b, right? Okay. Right. So, what is the summary of today's class? First, you studied signed magnitude and ones complement. So, signed magnitude, it is having sign plus magnitude. Ones complement is inversion between zeros and ones. Both suffer zero problem. Both having plus 0 and minus 0. I mean the dual 0. So, that's why you tried, to overcome this particular problem, we are following this 2's complement. 2's complement is a universal standard as well as the industry standard. Here it is having single zero and one circuit is enough for doing the addition operation as well as the subtraction operation. That circuit is also the adder circuit. Okay. After that you studied what is IEEE 754 standard. This IEEE 754 stores real number as signed, biased exponent and mantissa, just like a scientific notation in binary. Okay. So there it is having two precision. One is a single precision 32-bit and another one it is a double precision 64-bit. We compared everything based upon the storage as well as other parts also. Try to work on this because these are the practicing questions I have given. Represent minus 18 in 8-bit sign magnitude, 1's complement and 2's complement, and find what are all the changes happened between the sign magnitude to 1's complement and 2's complement. And the second question I have given is, why can 2's complement represent one extra negative number versus positive? Please try to find the answer for that. And try to convert this minus 6.25 into IEEE 754 single precision format. In our example, we tried for plus 10.5, but here I have given you the negative value. And the last question, what bit pattern represents plus infinity in the IEEE 754 single precision? Follow the last slide, the special value slide. Okay, right? So till this, we completed what are the signed numbers and what are the three different signed numbers. I mean the three different schemes there in the signed numbers as signed magnitude, 1's complement and 2's complement. And we checked what is IEEE 754 standard for floating point representation. I hope this class is very much understandable for you. If you have any doubts or any queries, please post it. You will get the answers very soon. Okay. Thank you so much. Thank you for listening to the class.